Hello everyone. In this video we will do some examples for integration by parts for definite integrals. Let me just quickly recall that the integration by parts formula that we had before, u dv is equal to uv minus integral of integral of v du. This was for definite integrals. For indefinite integrals, when you have a definite integral on the left hand side, the right hand side must be a number as well, and the number you need to have is this, which equivalently this means that if your functions are function of x, you have ub vb minus evaluate u times v at the upper limit and then evaluate it at the lower limit minus another definite integral which needs to be evaluated using whatever techniques we have. Okay, let's do some examples here. Integral of x times 2 to the power x dx from 0 to 1. Remember that when we had a polynomial, so let me just write here, polynomial to e to the power x, e to the power mx, we know how to deal with this. You can do exactly same thing here with this 2 to the power x. One reason is that you can rewrite this integral as 0 to 1 x. 2 to the power x is the same thing as e to the power ln 2, a constant, times x. So you have again a polynomial times e to the power mx, and you can do the same thing. So that's one way to go, but I will, in this video, I will just go the straightforward. So for my integration by part, the pattern I have is I will take u to be x, and then dv to be 2x dx. Okay, then du is just dx, 1 times dx, and v is integral of 2 to the power x dx. Remember that integral of, in general, so this is maybe another thing to recall, that integral of b to the power x dx is b to the power x divided by ln of b. So in this case, I have 1 over ln 2 to the power x. Now that I have all the components, I can go ahead 0 to 1 x to the power x dx is going to be equal u times v. So x 1 over ln 2 to the power x go from 0 to 1 minus integral of v times du 1 over ln 2 to the power x dx, and go from 0 to 1. This is definite integral. One thing that you have to be careful here, that this is not ln of x, it's just a constant. 1 ln 2 is the constant, ln of 2 is just constant. Okay, let me evaluate the first one, means that evaluate the function at the upper limit. This will be 1 times 1 over ln 2 to the power 1 minus evaluated in the lower limit 0 times 2 to the power 0 over ln 2. So that is the first part. The second part here, what is integral of 1 over ln 2 to the power x? 1 over ln 2 is just a constant. So here's, let me put that there. Then integral of 2 to the power x is 2 to the power x over another ln 2. So ln 2 here, I have to square it. That's antiderivative. This is definite integral. You go from 0 to 1. Okay. So what we have here then is the first term here. This one is just 2 over ln 2. This part, the whole thing is 0, so I don't need to write anything there, minus. If I plug in a 1 in this term, so this will be 2 over ln 2 squared, minus, plug in 0 there, 2 to the power 0 over ln 2 squared. So what we have, I can find the common denominator. These kind of simplifications you are supposed to do or able to do. This will be 2 ln 2 minus 2. This minus needs to be multiplied both there and there, plus 1. Okay, so another simplification, I can bring it down inside and put it as power. So 2 to the power 2 is 4. This is ln 4 minus 1 over ln of 2 squared. That's the value we have for that specific one. Okay. The second example is one of the examples that we have done it before. I will do it a little bit quickly, this one here as well, just as an example, more example. If you have tan inverse, take u to be tan inverse of x. dv is going to be dx. From there, you can see that du is 1 over 1 plus x squared dx. If you haven't watched the video for tan inverse, please go back and check that, because I will go a little bit fast here. So my integral here will be integral of tan inverse x dx from 0 to 1. And we know that this is a uv, which is x tan inverse x. So you're going from 0 to 1 minus integral 0 to 1 of v du, which is x over 1 plus x squared dx. And as we saw in the other example, the substitution u equal to 1 plus x squared will solve that last thing for us. Let me just evaluate the first part. And for the second part, what we will find is that this is half of 1 plus x squared, going from 0 to 1. And well, tan inverse of 1 is pi over 4. That part is 0 minus half of a ln of 1 plus 1, which is ln 2, minus a ln of 0, which is, ln of 1 plus 0, which is ln of 1. Yes, so this is 0. So what we find here is pi over 4 minus half of ln 2. Well, we can use properties of ln and take this as a power up there, and what we will get is minus ln of root 2. Okay, and the last example here is find the average value of the function x cosine 2x on the interval pi over 6 to pi over 2. Very nice. So first thing to recall is that average value of an integrable function f on interval ab is this number, 1 over the length of the interval integral of the function on the interval. So for us, in this case, the average value or the value that we are trying to find will be 1 over pi over 2 minus pi over 6. That's the length of interval. Integrate pi over 2 to pi over 6 to pi over 2 x cosine 2x dx. So we have to evaluate this integral and plug in there. So I'll go separately and think how to integrate this piece here. And this is a polynomial times cosine mx. Remember, in those cases, we take u to be x, the rest to be dv. So let me just write our integration by part preparation steps here. So u is x, dv is cosine 2x dx. From there, you see that du is just dx, and v is integral of cosine 2x dx, which is half of sine of 2x. Okay, now that I have everything there, now I apply the integration by part. U times v, x times half of sine 2x, go from pi over 6 to pi over 2, minus integral of pi over 6 to pi over 2 v du. So this is going to be half of sine 2x dx there. Well, the first part means that, okay, I need to evaluate that there. 2 times pi over 2 minus upper limit, then minus evaluated at the lower limit. So 2 times pi over 6. That's nice. Minus, well, I know that integral of sine mx is negative 1 over m, so this will be plus 1 over 2 was there before. Integration of sine of 2x will give me another 2. That will be 1 over 4 cosine of 2x. And I have to go from pi over 6 to pi over 2. So as I go, I will evaluate this. This guy here will be pi. Sine of pi is 0, so that will go away. Here I have negative pi over 12, and this is what? This cancels with that. This is pi over 3. Sine of pi over 3, or sine of 60 degree, is root, oops, let me do it with root 3 over 2. That's the first part. The second part is you do half of cosine of 2 times pi over 2 minus 1/4 of cosine of 2 times pi over 3, pi over 6. Okay, so let me write this pi root 3 and then 24 plus. You see, these two cancel, just get cosine of pi. Cosine of pi is negative 1, so that will turn 1 over 4 to negative 1 over 4. And here I have pi over 3. Cosine of pi over 3, or just cosine of 60 degree is half. So I will have 1 over 4 times 1 over 2. So what we found is negative pi root 3 over 24. Why both of them are negative? Yes, because cosine pi was negative. So this one, if I find the common denominator, that will give me 3 over 8. And let me find another common denominator. That way, minus pi root 3 minus, I have to multiply that by 3, then that's. So that is the integral we have there. Now, if I found the value of this guy, which is, 3 minus 2, which will give me 2 pi over 6. Sorry, and that is just pi over 3. So this will be 3 over pi, the inverse of what we found. And the integral, the value we found is negative pi root 3 minus 9 over 24. You can simplify. Yes, we can. And you get, what numbers we get there? Here is, that simplifies with that. Oh, this is simple now. This is 8 pi minus pi root 3 minus